As a member of Yonsei University, I would like to thank you all the audience and speakers participating in this conference. And I'm also very honored to have this opportunity to present some recent result. So today, I will talk about the subspace time evolution in parameterized quantum circuit. So this work is established based on the variational quantum algorithm framework. So I think many of in the audience are already familiar with this framework. So I'll briefly introduce this concept, and then I will introduce our main result, and I'll show you some examples. Ising model, 2-qubit Ising model, and 10-qubit models. However, I'm very happy to present some experimental data obtained by the Yonsei University IBM quantum processor. And then I will conclude with some summary. So as I said, our work is developed based on the framework of a variational quantum algorithm that is also known as VQA. So VQA is composed of those 4 steps. So at the first time, we should prepare some quantum states in the circuit, and then we measure some observables and estimation to estimate cost function. And then by using those some experimental data, we can classically perform some post-processing, such as averaging over those data, and also we performed some classical optimization. Actually, those classical optimization is already developed in machine learning or some numerical techniques, such as a gradient descent. So in this sense, the VQA, when we implement those VQA, quantum computer is dedicated to obtain a prepared quantum state and estimate cost function, because quantum computer provides some exponential speed up or some efficient method to perform those 2 steps. And on the other hand, a classical computer can dedicate to perform those 3rd and 1st step. So VQA has many applications, because by adjusting some cost functions, we can apply this method to various fields. Actually, at the first time, the variational quantum eigensolver was introduced to attack the ground energy estimation. That is so-called variational quantum eigensolver. And then this framework is extended to attack some very challenging problems, such as applied mathematics and some quantum machine learning and some quantum dynamics. So in this talk, I would like to focus on this quantum dynamics problem. And however, I think recently there are many researchers are working on verifying some complexity of this VQA. However, fundamentally, it is very challenging to verify how much computing resource are required to perform this VQA, and there is a quantum advantage or not. There are many challenges. That is because this method depends on the choice of ansatz and then some optimization techniques. And also there are many problems or challenges in those, such as local minima. So even if the optimization procedure is finished, actually we cannot say that it's definitely global minimum. So as far as I know, I think it's also another very hard, difficult problem to verify that. And also some noise effect or some cost function estimation is also very critical. However, the most recently, many researchers are focusing on to investigate how much balance plateau has occurred during this optimization. Because if there is a balance plateau, exponential increase of sample complexity is required. So I would like to remark that in this sense, when we implement VQA, we should care about those factors, including our method. So in the quantum simulation, actually, at the first place, the Feynman conjecture that quantum computer can be useful to simulate some quantum systems. And so L.O.V.E proved that the quantum computer can efficiently simulate those kind of some Hamiltonians. Yeah. And then some other approaches has been developed to cover some various type of Hamiltonians, and also another to reduce the complexity. Yeah, however, in this work, we will focus on this totalization because it is relatively easier than other methods, and also it's very intuitively we can implement in real hardware. So, for instance, in the Ising model, the totalization is very intuitive because Ising model can be described in this way: two-body interaction and single just rotation. So in the first order totalization, each local Hamiltonian can be performed just in this way, decompose Hamiltonian into local Hamiltonian, and we perform those interactions. And so each interactions can be also implemented in the real hardware by using those quantum gates. And so, yeah, if we implement those totalizations in real hardware, the quantum circuit would be like this. So we prepare some initial state, U0, and then we perform those total step and repeat again until it achieves some target precision. Yeah. However, as far as I know, I think it is still difficult to implement this totalization in real hardware. So variational quantum algorithm is developed to reduce that kind of a computing resource. So our main concept is that we prepare some initial state first, and then we apply a parameterized quantum circuit here. Then we implement the totalization step only one. Then only one or two, so it depends on some quality of hardware. So after we apply this total step, then the state is evolved to some state that is evolved to within the time delta t, because we decompose the total time evolution into some small time step delta t. So, however, if we repeat this total step, I think it would be very many noises involved. So we introduced the inverse of initial state preparation. Then by measuring in computational basis, then we can obtain the fidelity. The fidelity corresponds to the probability of obtaining these all zero outcomes. So the reason why we pick up this fidelity as some numerically investigating the distance between two states is because that the fidelity is relatively simpler than other distance. So our cost function looks like this. So by optimizing this phi to minimize this fidelity, And then we obtain some final value parameters, and then that parameter can be used to prepare the new state. But this new state is close to this evolved state. Yeah, however, I would like to remark that this kind of method is not my own idea. Already there are many previous works to attack this kind of approach. Yeah, however, our main point is that the previous works mostly focus on the time evolution of just one initial state. So if we want to simulate another state, we need to repeat the whole procedures. So we would like to develop some method to simulate a subspace expanded by those some orthogonal base. So in order to do that, we need some more circuits. So first of all, we prepare the one of the bases of psi 0 here, and then we repeat the same as the previous circuit. And however, we need more circuit to cover the subspace. So we prepare another psi 1, the U1, by applying the U1 unitary. However, the rest of the circuit should be the same as this one in order to cover at the same time. And additionally, in order to adjust some update properly the phase of between two states, so we need to introduce the psi plus, that is superposed state of psi 0 and psi 1. And the total host function is defined as in this way. So the first part is dedicated to allow us to simulate this first column, and the second second fidelity is dedicated to find the optimal value, optimal those column vector. And the third one is important to adjust this phase vector. Then by optimizing at the same time, we can cover all the subspace. That means alpha psi 0 and beta psi 1. Yeah, every arbitrary state in this subspace can be simulated in the optimized parameter quantum circuit. So one of the particular some positive aspect of this method is that we can verify the quality of this optimization procedure. So as far as I know, the user just VQA have no those kind of some lower bound, the performance of lower bound. Because that, as I said before, we don't know that the solution is in local minimum or global minimum. However, in this case, our cost function is composed of those fidelity. So we know that the fidelity is the limited, the maximum fidelity is 1. So by considering all the data obtained during this optimization procedure, then we can obtain the final fidelity of the lower bound of fidelity that obtained by the parameterized quantum circuit. So yeah, that is some positive point of our method. And then we can generalize to arbitrary some subspace. Yeah, if the dimension, the number of base expanding this subspace is n, then the total fidelity that we have to measure, fidelity is the number of this fidelity is 2n minus 1. So yeah, it linearly increases with respect to the number of bases. So it's our some preliminary result. So we test in Ising model, 2-qubit Ising model. So as you can see, if we perform the subspace, we assume that our ansatz is SU4 for 2 qubit. That means it is perfectly express all the states in 2 qubit. So yeah, that expressibility is maximum. Yeah, in this case, the subspace time evolution shows the maximum fidelity one. So all the fidelity are overlapped here. So we just can see that some one line. However, all the fidelity, including psi 1, psi 0, yeah, all fidelity are 1. However, if we only optimize for just the one initial state, then other states, such as if we focus on the 0, state time evolution, then 1, state is not evolved perfectly. So that means it's almost random. So that's the reason why we have to care about the subspace time evolution. So if we restrict our some expressibility of ansatz by just the GXG and C0 gate, and in that case, the fidelity is decreasing as time is increasing. So yeah, that's because of the limited expressibility of this ansatz. So this is our some IBM quantum processor result. So we performed the 2-qubit experiment in Yonsei University IBM quantum processor. Yeah, and then we almost we demonstrate the experimental result, almost followed some simulation. And so another application of our method is that we can, by optimizing the parameterized quantum circuit, just one whole procedures, we can generate all arbitrary state in subspace. So we tested by from 0, state, 1, state. So I think it's very small, but the x-axis is time, and the y-axis is theta over 2-qubit state, 0, plus and 1. So when it has theta is 0, then there is no entanglement here. However, when it is pi over 2, entanglement is maximized, and then it disappears. So this is the exact solution, and this is the result from throttleization. That means just the emulation result. Then is experimental result. So I think it's very coincide with some numerical data. Yeah. So what I want to emphasize in this result is that we can apply those some already developed method. So if we want to investigate some entanglement dynamics, so we need to compute any state. We need to compute numerically. However, if we can prepare a quantum state in quantum circuit, then we can perform those techniques. So in this sense, it is just a constant depth to estimate the entanglement. So just we optimize, finish the whole optimization procedure, and then we can explore any arbitrary state, entanglement of arbitrary state in this subspace. So, yeah, we considered some more entanglement, some more qubit case. So we 10-qubit hardware and 10-qubit Ising model. So in our ansatz is defined in this way, and yeah, I just skip. Yeah. So yeah, it's it shows the whole procedure. So yeah, it's from 1 layer to 5 layer, actually, according to the number of layer, we can adjust some expressibility of ansatz. So, yeah, we can expect that because of expressibility, so one layer ansatz, its fidelity is decreased very fast. Yeah, however, by increasing the number of layer, we can see that the fidelity is stable, almost around 0.98. Yeah. So, yeah, I would like to summarize. So we developed some variational quantum method, quantum algorithm for simulating the evolution, time evolution of a subspace, and we tested it in some Ising model and IBM's quantum processor. And there may be some open questions. So can we, yeah, a relationship between the number of qubits and needed layers to achieve high fidelity and finding a better ansatz based on the symmetry in Hamiltonian. Thank you for the attention.